My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. In this class, we will see critical thinking and problem solving on insulated end film. In last class, we discussed the uh, heat conduction in fin, rectangular fins. There are three types of the fins. Last class we saw the and we discussed on long fin. Okay. So in this class, we will see heat conduction in insulated end film. Okay. So we'll derive the heat heat conduction in insulated end film, and we will see a few more numericals on this insulated end film. Okay. We know that importance of fins. Last class also we discussed the importance of the fin. So it is a extended surface which is added to inadequate surface to increase the or to enhance the heat transfer rate from base surface to atmospheric condition. The main purpose is to the application of these fins in cooling purposes. These types of fins attach on the some transformers to reduce the heat of the transformer and to reduce the heat of the automobile engines, just like in bikes, as a radiator in cars. So many applications are discussed in previous class also. Now we'll see derive the heat conduction equation of insulated end film. Okay. So in last class we already discussed the heat conduction equation in for the long fin. We'll see what is insulated end fin. Insulated end fin is nothing but a short fin. Okay. So it has particular length or finite length. So fin with insulated, it may be seem undesirable to use a fin with an insulated tip, since insulation will decrease the heat transfer from the fin. So however, in practice, the heat transfer area at the fin tip is generally small in comparison with the lateral area of the fin. It means, so this is the base surface. You can see this is the fin. At the end, the heat transfer rate is very less compared to the heat transfer by surrounding surfaces by convection process. Okay, here the conduction process. So under these conditions, the flow of heat at the tip is negligible. This condition can be mathematically expressed as the rate of heat transfer with respect to direction is equal to 0. It means at x is equal to L. L is the length of the fin. At the end of the fin, the heat transfer rate, the change in temperature with respect to x is 0. Okay. So here we will see this uh, this condition as a boundary condition. Okay. You know that general heat conduction equation, which one already discussed in previous class. Okay. So this one, you know that d square theta by dx square minus m square theta is equal to 0. So it varies 0 to L. Length is the particular length. So you know that to theta we have taken t minus t infinity. Theta naught is nothing but to t naught minus t infinity. T naught is the temperature at base surface. T infinity is the ambient temperature, atmospheric temperature. T is the temperature at a particular distance x. Okay. At x is equal to 0, so T is equal to T naught. At x is equal to L, so we have to apply this condition. So this one is the first boundary condition. So at x is equal to L, we have to apply this condition. D theta by dx is equal to 0. So change in temperature with respect to x direction is 0. We have to construct this one. We will derive this heat conduction equation in insulated and see this one. So here two types of the boundary condition. It means so if you compare this one, heat transfer rate is gradually decreases. So this is dt by dx is equal to 0. So at particular stage, the heat transfer rate does not take place. It means there is no change in the heat transfer rate. So that is the d theta by dx does not change. It is equal to 0. So that one is the insulated and pin. Okay. We know that here there are two boundary conditions. One boundary condition at x is equal to 0. Theta is equal to theta naught. We know that theta temperature T minus T infinity ambient temperature. So T is the temperature at a particular distance x. So x is equal to 0 means theta shows the base temperature. You know that this is the surface. So this one is the short end here. So this is the temperature T naught. This one is the temperature T infinity. At a particular distance x, so T is equal to temperature is equal to T. You are taking small elemental area for derivation of this one. So through convection process, Q x entry, Q x plus dx is the leaving through conduction. Q convection leaving through convection process. You know this one, okay? So for this one, we derived this general heat conduction equation, that is theta is equal to C1 e to the power of minus mx plus C2 e to the power of mx, already derived in previous class. That is the general equation. Okay, and we have to take the two boundary condition. If we apply these two boundary condition in general equation, we will get to C1 and C2 value. And if you apply this C1 and C2 values in general condition, general heat conduction equation, then we will get the temperature profile, temperature value. If you derive this one based upon the convection process, then we will get the rate of heat transfer in that insulated end pipe. Okay. So here there are two boundary conditions. One is at x is equal to 0, at x is equal to 0. Then T is equal to T naught. T is equal to T naught. So it means temperature difference theta is equal to, then theta is equal to T naught minus T infinity. Theta is equal to T naught minus T infinity. At x is equal to L, at the end of this length of pipe. Okay. Here condition is equal to temperature difference with respect to x is equal to 0, because it is insulated end. At the end portion, it will be act as insulating end. Okay, heat transfer rate is nowhere, that one. So here apply the first boundary condition to general equation. We know that general equation theta is equal to C1 e to the power of 4. Okay. Just we are applying the first boundary condition at x is equal to 0, theta is equal to theta naught. Okay. Then e to the power of minus mx m0, e to the power of 0 is equal to 1. Then C1 plus e to the power of 0, that is 1. Here also e to the power of 0 is 1. Then C1 plus C2 is equal to theta naught. That is the equation 1. If you apply the first boundary condition, we will get equation 1. That is, so theta naught is equal to C1 plus C2. Theta naught, nothing but T naught minus T infinity is equal to C1 plus C2. So this is the first boundary equation by applying the first boundary condition. Okay. So next, apply the second boundary condition. Apply the second boundary. You know the formula. What is the general equation is equal to theta is equal to C1 e to the power of minus mx plus C2 into e to the power of mx. Okay. So theta is nothing but T minus T infinity. Temperature minus temperature at x distance minus ambient temperature is equal to this one. Okay. So second boundary condition, at x is equal to L, dt by dx is equal to 0. It means if you derivative this one dt by dx with respect to x, then d infinity, that is constant, it will be 0. We have to equal this one is equal to, we have to derive this one. It means t minus t infinity is equal to c1 e to the power minus mx plus c2 e to the power mx. This is the general equation. If you derive derivative with respect to x, you will get this value. Then you can equal that equation to 0. Okay. So derive this one dt by dx. So derivative with respect to x. Then derivative of this one e to the power minus mx means minus m into c1 e to the power of minus mx. And the derivative of e to the power of mx means m into c2 e to the power of mx. Okay. So according to the second boundary condition, dt by dx is equal to 0. You can equal dt by dx is equal to 0. You can write 0 in the place of dt by dx. Okay. Is equal to minus m into c1 e to the power of minus ml. So at x is equal to L, in the place of x you can write to L plus m into c2 e to the power of ml. Okay. So then c1 e to the power of minus ml is equal to c2 e to the power of ml. Then automatically c1 is equal to c2 into e to the power of 2ml. Okay. So this is the equation 2. So in the place of c1 in equation 1, if you write this c1 value in equation 1, you will get this c2 value. Okay. Here we can see here. So substitute the values in equation 1. What is the equation 1? C1 plus C2 is equal to theta naught. Okay. So you know that C1 is equal to C2. What is the C1? C1 is equal to C2 e to the power of 2ml. C1 e to the power of 2ml plus C2 e to the power of theta naught. Okay. Then you can take common C2 into 1 plus e to the power of 2ml is equal to theta naught. So here you can see. Okay. Then C2 is equal to theta naught by C2 is equal to theta naught by 1 plus e to the power of 2ml. Okay. So then you know that we got that C2 is C2 value. Then we have to find out the C1 value also based upon the equation 1. C1 plus C2 is equal to theta naught. Then you can find out C1 value. C1 is equal to theta naught minus C2. Okay. So theta naught minus C2, we know the value of C2. C2 is equal to theta naught by 1 plus e to the power of 2ml. So in which theta naught is the common term, you can take common. Then 1 minus 1 by 1 plus e to the power of 2ml, you can take 1 plus e to the power of 2ml as a LCM. Then we'll get this one. Okay. So 1 minus 1, just 1 minus 1 will be cancelled. E to the power of 2 ml by 1 plus e to the power of 2 ml. Okay. So this is the value of C1 value. Then you know that general equation, that is theta is equal to C1 e to the power of minus ml plus C2 e to the power of ml mx. Okay. So if you substitute the C1 and C2 values in general equation, you will get this equation. Okay. So then theta naught is equal to, so this is the theta is equal to theta naught into, in the place of C1 you can write the theta naught minus this one, theta naught into e to the power of 2 ml by 1 plus e to the power of 2 ml. Okay. So here just we will get this equation. Then we can simplify this one by like this one. It can be rewrite in more for the more compacting form by multiplying the numerator and denominator of the first term on RHS by e to the power of ml. So multiply e to the power of 2 ml with numerator and denominator. Then the equation will be like this one. So first term e to the power of ml, the second term will be multiplied by e to the power of minus ml. Then equation will be like this one. Okay. So here denominator is the same term, numerator is different. Okay. So denominator same means you can write one thing. So like theta is equal to theta naught into e to the power of minus ml plus e to the power of ml into e to the power of minus x minus l plus e to the power of m into x minus l. Okay. So e power x by e power minus x, e power minus ml by e power minus ml means these are the hyper ratios. So the value is equal, if you take this is by 2, this is the by 2. Okay. So e power minus x plus e power x by 2, that is the cos function, cos h m into l minus x by cos h into ml. So that is the formulas we already, hyperbolic functions formulas, you know that one. Okay. So this is the value. Okay. So if you derive this one, derivative with respect to x d theta by dx. Okay. D theta by dx is equal to this, you can send like this one, theta naught into minus m into sin h ml. Okay. So then derivative value is equal to this one. Okay. Then you know that according to uh, conduction formula, q is equal to uh, Ka into dt by dx. Okay. If you substitute here, then we will get that formula, rate of heat transfer. Rate of heat transfer Q is equal to, so K into A, Ka into, so dt by dx is the value, total value. You can substitute here. Theta naught into m into tan h ml. Okay. So here Ka into theta naught is nothing but T naught minus T infinity into m. M is equal to under root of hp by Ka into tan h ml. Okay. So you know that. So here Ka, here under root Ka, then this will be under root to Ka times. Then the equation is Ka. Equation hp under root of hp Ka into, this is the uh, theta naught into tan h ml. So this is the final equation. For the long pin, so up to this under root of hpk into theta naught. For the insulated end fin, the formula is under root hpk theta naught into tan h ml. One more fin is there, that is the convection of the end fin. Just here I am not deriving that one, just I am giving the final formula for this one. So finally there are three types of the fins. One is long fin. So just very long length. We are assuming that x is equal to length of the fin, x is equal to infinity. We are considering that one. So the formula for long fin, rate heat exchange in the long fin, Q is equal to under root of HPK into theta naught. So next one, fin with insulated end fin. Insulated end fin. So short fin, nothing but. So Q is equal to under root HPK theta naught into tan H ml. Okay. Similarly, fins with convection of the end. Convection of the end. This is the formula under root HP theta naught. This is the same term into tan H ml plus H by mk by 1 plus H by mk into tan H ml. So these are the formulas. We have to remember uh, these formulas for solving different numericals which are based upon the long fin, short fin, and convection of the end fin. Okay. So here we will see few numericals based upon this one. Already this is a very long fin, so you know that Q value under root of HPKA into theta naught. Theta naught is nothing but HPKA into T naught minus T infinity. Okay. If you know this formula, you can solve this numerical. In last class already discussed this one, derivation of this one. So very long fin, diameter of the long fin also given. So D is equal to 25 mm. So 0.025 meter. That is the dia. Then the copper uh, fin. The material of the fin is copper. Thermal conductivity of the copper is equal to 380 watt per meter Kelvin. Extended to a surface, initial surface base temperature T naught is equal to 120 degrees Celsius, and ambient temperature, air temperature T infinity is equal to 25 degrees Celsius. Okay. Heat transfer coefficient H is equal to 10 watt per meter Kelvin. Okay. So we have to find out the heat loss Q value. Heat transfer through or heat loss through this way. Okay. You know this formula under root HPK into theta naught is equal to under root of H value. H is the value the given 10 into P is the perimeter. So perimeter of the round fin, it means pi d. That is the pi into diameter T into K is the thermal conductivity 380 into area. Area is equal to pi by 4 d square. Okay. So you know that value of D 0.025. So here we can substitute 0.025. Here also we can substitute 0.02 into T naught minus T infinity. T naught is 120 minus T infinity is the 25. So if you substitute the values, then we will get the heat loss from this thing. Okay. So in this process, we can solve the numerical. We'll see one more numerical, which is based upon the convection of end. An aluminum alloy fin. The fin material is aluminum. So of 7 mm thickness, T has been given 7 mm converted to 0.007 meters, and 50 mm long. So short fin, L is equal to 50 mm converted to meter 0.05. So meter. Okay. Thickness and 50 mm long, which is maintained at a temperature. So T naught is equal to 120 degrees Celsius. The ambient temperature T infinity also given 22 degrees Celsius. The heat transfer coefficient and the conductivity of the fin material. So both are given. Thermal conductivity, heat transfer coefficient to thermal conductivity is equal to 55 watt per meter Kelvin, and heat transfer coefficient. So heat transfer coefficient H is equal to 140 watt per meter square. So these values have been given. Okay. Determine first temperature at the end of the fin. Temperature at the end of the fin. Okay. So at the end of the fin, the temperature at the end of the fin means at x is equal to L. So what is L? 50 mm. So at 50 mm distance, we have to find out the temperature. Okay. So T minus T infinity by T naught minus T infinity. You know this formula. Okay. So theta naught into cos h ml minus x by something. You already derived that one. You can take that formula. Okay. Next one, we'll see temperature at the middle of the fin. Middle of the fin means 50 by 2. Distance x is equal to 25 mm. Next, total heat dissipated by the fin. So Q, you have to find out. Okay. So temperature at end T at x is equal to 50 mm. T at x is equal to 25 mm. You have to find out these values. Okay. We'll see one by one. So these are the given data. We can consider thickness T is equal to 7 mm is equal to 0.007 meters converted to meters. Length 50 mm 0.050 mm. So base temperature, so T naught or TB, anything, T naught is equal to 120 convert into Kelvins 273. So 393 Kelvins. Ambient temperature T infinity 22 plus 273 295 Kelvin. Okay. Heat transfer coefficient 140 watt per meter square Kelvin. Thermal conductivity 55 watt per meter Kelvin. Okay. So the length is 50 mm means we can consider it is a short pin. So short pin means insulated end pin. So we have to use the formulas which are related to insulated end pin. Okay. So we know the temperature distribution in short pin or end insulated end pin. So the temperature distribution formula, you know this one, that is T minus T infinity by T naught minus T infinity is equal to cos h m into L minus x by cos h ml. Okay. By using this formula, you can find out the temperature T at x is equal to 50 degrees, 50 mm. Next to it means full length. The temperature at the middle of the fin also you can find out by using this formula. You have to remember this one. Another one for the last third point. So Q is equal to under root of HPKA theta naught into tan H ml. Tan H ml. This is the formula. By using this formula, you can find out the heat dissipated by the fin. Okay. First, we will see temperature at end of the fin. Okay, temperature at the end of the pin. So end of the pin means x is equal to L. You can take x is equal to L. In the place of x, you can write the L value. Okay, L is nothing but 0.05 meters. You know that temperature formula T minus T infinity by T naught minus T infinity is equal to cos h m into x minus L minus x. What is that one? L minus x. L minus x by cos h ml. So this is the formula. Here x is equal to L because full length. So then T we don't know. We have to find out this one. T infinity, that the value of T infinity is equal to you know that the T infinity is equal to 295 Kelvin you can take. So first of all we will solve this one. Here in the place of x you can write L, then so cos h m 0, so cos 0, so cos h m 0, cos 0 is equal to cos h 0 is equal to 1 value, then 1 by cos h ml. So you can take this formula. Then here we don't know t, we have to find out this one. T infinity we know that, t naught we know that, t infinity we know that. So L also you know that. You have to find out the m value. What is the value of m? M square is equal to hp by k, you know that's one. Then m is equal to under root of hp by k. So you have to find this value. Okay. So under root of h value also given, that is nearly uh, h is equal to 140 into perimeter. So perimeter is equal to uh, p into, so 2 into actually width. It means W plus L you can construct width into thickness. So here width not given. So you can take length here direct. So 2 into L. 2 into L is equal to 2 into 0.050. So we can take like this one. So this is G into 0.050 by K thermal conductivity. Thermal conductivity value also given 55. So 55 into area. So area you have to find out length into thickness. You know that area at the end of the pin. So that is 0.050 into 0.007. Okay. So if you solve this one, you will get value m value. That m is equal to uh, just you can take m value. Yeah, m is equal to 26.9. Okay. So then you can substitute this m value in this formula. So in this formula, t minus t infinity by, so t naught minus t infinity, t naught minus t infinity, cos h m into L minus x. So we already derived this one. So this is the L, this is the 0 means 1, cos h into here m value is equal to 26.9 into L value, this one. Okay. So the cos h into this value, that is the value is equal to 1 by 2.05. Okay. So then substitute the t infinity value 295 and t naught value is the 393 value and the t infinity is the 295. So if you substitute all the values, then we will get the t value. So this is the temperature T 342.8 at the end of the pin. End of the pin. It means at x is equal to L. At x is equal to L means L is equal to 50 mm length. This is the temperature. Now we'll get the, so this is the temperature of the end of the fin. So Tx is equal to L. This is the value. This is first point. Now we'll see second point. At x is equal to L by 2 at the middle of the pin. What is the temperature of the middle of the pin? So we'll see the temperature of the middle of the pin. So x is equal to L by 2, 0.050 by 2. Then x is equal to 0.025 value. Okay, you can take that one. Here, just if you substitute this one, L minus L by 2, you know the value of L 0.050 minus 0.050 by 2. So then you know that value of m value. If you substitute all the values, then we will get the temperature T. T infinity, T naught, you know that, and cos h, m value also 26.9. Already find that one. Hmm. So by using the m is equal to under root hp by k, you know all the values. Then if you substitute all the values in this formula, we will get the temperature. So this is the temperature, the value at x is equal to L by 2 temperature is equal to the 354.04 kelvins. So this is the value. So in this way, just we can find out the temperature of the fin at any point by using this temperature ratio values. Okay. So the temperature at the middle of the fin is equal to 354.04. Then last point you have to heat dissipated by fin. So you know the formula for this one. So under root of Hp Ka into theta naught. Theta naught is the T naught minus T infinity into tan H ml. Okay, you know that m value 26.9. So this is the value, temperature 393. This is the value. This ambient temperature 295. M value and L value the 50 mm. It means 0.050. If you substitute all the values, H value you know that, P also you know that, K also, area also you know that. Okay. If you substitute all the values, you will get to the heat dissipated by the fin. Q is equal to 44.4 watts. So in this way, just you can solve different numericals which are related to insulated end fin. Okay. So these are the different textbooks we can refer these textbooks to solve different numericals which are related to insulated end fin or different fins, long fin or convection of the end fin also. Okay. Thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.